Okay, so here's example 9. So we've got a thorium nucleus decaying into a radium nucleus and an alpha particle, which is a helium nucleus. So these are all nuclei, and these are the masses of all the nuclei. The mass of the alpha is the mass of the helium nucleus. So the thorium decays into radium. Why does it do that? Well, because radium has a higher binding energy per nucleon. It's more stable, okay? So by undergoing this radioactive decay, the thorium is producing an element, or a nucleus in this case, that is more stable, okay? So when the thorium decays into radium, the balance between the strong and the electromagnetic force in radium is better, should we just say, okay? It's a better balance of forces there, and it results in a more stable nucleus. It results in the nucleons of the radium nucleus are more tightly bound, okay? They're bound more tightly together, and that means that they enter a lower energy state than the nucleons in the thorium, and that means that they release energy, okay? And the energy then is given to the radium and the alpha particle as kinetic energy. And because energy is released and this enters a lower potential energy state, the nucleons are more tightly bound, as we said, and it's got a higher binding energy per nucleon. So the whole process is energetically favourable. So now we're going to work out the actual energy released here. I've already told you where the energy goes. It becomes the kinetic energy of the particles that are produced, or the nuclei that are produced. So to work out the energy released, we need to know the mass on the left-hand side. Well, on the left-hand side, we've only got a thorium nucleus. So remember, these masses are the nuclei, so we don't need to worry about any electrons in this case. Okay, so the left-hand side, 227.97929 U. The right-hand side is the mass of the mass of the radium nucleus plus the mass of the helium nucleus, or the alpha particle. Okay, and that's going to give us 227.9734 U. Okay, and then we can work out now the mass defect. So you can see the mass of the product is less than the mass of the original nucleus. So to work out the mass defect, we just take away the original mass. Sorry, take away the final mass from the original mass. And there must be a 0 on the end of that. And that's going to give us our mass defect, and our mass defect will come out as 227.97929, take away 227.97340, and that's going to be 0.00589 U. Okay, and then we can work out the energy. So we know this is the mass defect. That's the amount of mass that has been lost, so to speak. Now, it hasn't been lost because it's been converted into energy. Now, we know that 1 U is equal to 931.5 MeV. So if we multiply this mass defect in U by 931.5, we'll get the energy that's released in mega electron volts. And it comes out as 5.487. 5.487, I believe. So let's just check that. Times 931.5. So 5.487, yes, okay, and that's mega electron volts. There we go.